electrons and the electron. Oh, you see that? Yeah. Grab the wrong pen. So the issue then becomes, how do you configure this so that you understand what's the acid, what's the base? So given the structure that you have, so here's a set of single bond methyl groups, and then you have oxygen and a carbonyl structure, and this is the peptide structure. And now we're not going into a lot of detail here in terms of ability to hold on to hydrogen, or to put it another way, the removal of electrons making the hydrogen more positive. Right? So you have issues related to, is the element of the hydrogen is attached to electronegative or not? More electronegative than hydrogen. If it is, are there secondary issues such as resonance? Are there other issues such as inductive effects? Are there other issues such as hybridization? So let's look at this. Here's a situation in which you have two different hydrogens. So in this hydrogen, it's pair of electrons here. You should always think these days about filling in the electron pairs so that you can configure any structure that you need to look at with respect to where are the electrons coming from, where are the electrons from. Okay? Well, both of these are electronegative elements. So we might then say, let's look at the electronegativity value in and of itself. So obviously, oxygen is more electronegative than nitrogen, so immediately you might think this. And that would be a good choice, but you also want to think of something else too. And that is this consideration. Do you have any issues related to stabilizing the base here? And by stabilizing the base, we mean stabilizing the conjugate base. So in this case, if you pull the hydrogen off, you have, I'll rewrite this little piece right here, you have, I'll just put this as R for a moment, you have the possibility of resonance, right? Everybody could write the resonance form for this. It should not be a major issue, right? You have a pair of electrons going here, a pair of electrons coming like this. So now you're looking at a resonance form that gives you this back and forth. So therefore the conjugate base is further stabilized by resonance, so that adds to the strength of this acid. Still with me? Okay. By the way, over here, this is a special kind of linkage that, for those of you interested in medicine, this is a peptide bond, or an amide bond, as it's called many times in organic chemistry. It's a peptide bond, that's the term used in biochemistry and a lot of other bioengineering, etc. The reason this is special is because this is not really a single bond because of its resonance. Because you can draw a resonance form here. If you draw the resonance form here, it goes like this, right? And without drawing all the other pieces in, let's put this as R for a moment. This becomes not a double bond anymore, right? But it becomes a single bond like this with a negative charge. Now this is a double bond over here, and this is a positive charge. By the way, that's the other reason why this hydrogen isn't so easy to pull up. Okay? Because in doing so, you would have to reconfigure this little resonance form here, so that makes it more difficult. Right. How are we doing, ladies and gentlemen? Everybody okay with this so far? Everybody understand why this is the most acidic, is the carboxyl in the end? Any questions? Okay, so you're all experts on that now, right? The next piece is, what's the product of this reaction? And here, you're looking at a classic acid-base, Lewis acid, Lewis base, electrophile, nucleophile type process. And this electrophile, nucleophile issue is going to crop up again and again. So here, I'm going to rewrite it. Here's the sulfur. And here are the methyl groups attached Now, sulfur is like oxygen. It's in the same family, the same group. What's the big difference between oxygen and sulfur? Well, sulfur has more protons, has more electrons than oxygen, but the electrons are further away from the nucleus than they are in oxygen. So the net electromotive force, if you will, between that collection of electrons out here in sulfur, all the way back to the nucleus, through all of the other electrons that are there, that means that set of electrons, I'm kind of waving my hands because I'm not going to do the math, is less tightly held than they would be if they were closer. So therefore, they are much more easily manipulated, if you will, and so they become more nucleophilic in that sense. And in fact, sulfur in this case is going to provide a pair of electrons that are available, and what you have with boron is, I shouldn't have drawn it at 90-degree angles, I should have put it at equal distance, but I'm swapping it, is a structure in which you only have 3 electrons in the outer valence shell, so consequently you can have 3 bonds, but there is a space. Remember, you can make octets in that first row. There's a space available, so this pair of electrons can enter that space, and now the pair of electrons is literally shared. So now we have this. And what's over here? Boron, Cl, Cl, Cl. And what's the charge on sulfur? Positive. What's the charge on boron? Negative. Congratulations. That's called an adduct. Yes, ma'am?
Does the chlorines around the boron as well be a little electronegative?
They are very electronegative. As a matter of fact, that's part of the reason that this boron has such an attractive quality to electrons, and that makes this a very strong Lewis, what?
Base.
Is it an acid or a base? I didn't hear that. What was it?
Acid.
Acid. Why is it an acid? It is an electron
I'm not sure.
acceptor. Right? Acids accept. Think of it this way. Acids accept. Right?
No, this one.
And
Because acid
this is a fairly
accept. So
strong Lewis
this is the acid.
acid.
Yeah, this
A
is
really
this.
strong Lewis acid is this. It's a very strong Lewis acid. In fact, if you throw this into water, yeah, it does. It actually reacts very violently with water. The oxygen from the water is attracted to this, right? And it forms a bond with it right away, and then releases H plus into the oxygen, into the water environment. Of course, it then becomes a weaker acid. But the key is the acids are picking up electrons, and the base is sharing electrons. It's also true, one other side note here, this little configuration with sulfur donating electrons happens a lot, and you've probably been in the vitamin store or on the shelves at the Safeway, and you see something called SAM, SAM. You ever see that stuff sold in the grocery? You've never bought vitamins or S-adenosine methionine?
Oh, that.
Oh, that, yeah. It's, it's the verbiage on it is it's the greatest thing since beer in a can, and you want it for your good health, etc. Actually, we all have S-adenosine methionine in us, because methionine is an amino acid. I won't go through all of the structural configurations. Suffice to say that, this is R here, methionine has on it this kind of a configuration. So it's a thioether, just like that's a thioether. And what happens is, it has this tendency through the kind of reaction you just saw over there, except I won't go through it this day, but we'll go through it eventually. It forms this, and this has a positive charge on it. Now, why is that interesting? Well, because there's a methyl group and a methyl group and a positive charge sulfur. This allows this kind of a structure to come up to some nitrogen, typically found in DNA. Okay? And it's attracted to a positive center, which is attracted to this pair of electrons like this. So now this is methylated. So you get methylation of DNA. And you may have heard of epigenetics, perhaps. Epigenetics has to do with what happens to the genes after someone is conceived and born, etc. There is methylation, demethylation, turns some genes on, turns some genes off. And if you've been following, if you're here in the latest news item, a group of 400 researchers has just identified 4 million new sites on human DNA which have nothing to do with protein synthesis but have everything to do with controlling what another gene does. All because of things like this. All because of methylation. All because of sulfur transferring this methyl group, all because sulfur can act as a Lewis base. Congratulations.
Before you go too further, like,
What? I was going to go into DNA synthesis next. What?
I was just curious, at what point would boron connected to 3 same atoms not take on a 4th bond? 'Cause
Almost never.
Okay.
In fact, it's a real nuisance. Boron is both a blessing and a curse. How's that? Because what it does is, because of that empty orbital, it makes these boron compounds very, very structurally unique in terms of position. Now, you may be familiar with this. That's correct. This is boric acid, typically what you find in now in borax. That's the sodium salt of this. Okay, that's pretty stable. But the minute you put like this on it, okay, you say, well, this exists only for a short time and in very dilute solutions, because the first thing that happens is the boron, this space over here is very open to picking up electrons. In fact, in this case, boron does something really bizarre. We don't tell you about this. How many bonds to hydrogen here? 2. They're called banana bonds. We lied to you earlier and we tell you that hydrogen only has a valence of 1. But boron hydrides, which you're going to run into because we're going to use them in synthetic steps, there's actually a sharing of those pairs of electrons by 3 atoms as opposed to 2 atoms. So things become more interesting here as we go along. But since you asked about boron, I thought I'd tell you. Okay, other questions? Let's go to the next question. But you're always going to think of boron chloride, boron fluoride, etc., trichloride, tribromide as in Lewis, what? Acid. Right? Yes, sir. Quick, hurry up, come on, I got things to do. Can you what? Thio is the old term for salt. So we have an alcohol, it's a normal. If we have a thiol, this is ethane thiol. By the way, it stinks. Okay, next. You don't want to get thiol spilt on you, really nasty. Okay, next one says what? Is that number 4 next? Yes. Oh, number 3. Sorry. What's the pKa for a compound with a Ka of 10 to the 2? -2, right? What should go in the box on the right-hand side? Quick! HSO4 minus. Plus what? Somebody had their hand up over here? Okay, rank the acidity of the labeled protons in the following molecule from lowest to highest. Again, what hydrogen has an attachment to an electronegative element? Well, two of them do, so we can ignore HB because that's attached to a carbon. That one's not acidic, forget it. Well, based on the other two, not acidic. Two of them are attached to oxygens. That gives us a consideration over they're both the same, except the one on the right-hand side has an attachment to an oxygen, which is also attached to a carbon, which has another oxygen on it. Plus, it has resonance when you make the conjugate base. Question? Everybody clear about the resonance on that? Because it's a carboxyl group resonance. Okay.
Inductive and resonance?
Yes. That's right. Inductive and resonance. Okay, select the strongest base. Here's a way to think about it. What item here has the highest pKa as its conjugate acid? Okay, so the first one is hydroxide, which comes from water. The second one is hydrogen sulfide anion, which comes from hydrogen sulfide gas, H2S. Next one is the amide anion, which comes from ammonia. So of those three, which is the strongest acid of those three? Is it water, H2S, or NH2? Well, the strongest acid there is actually H2S because the sulfur has a tendency to make the water somewhat acidic, hydrosulfuric acid. Which is the weakest acid there? The ammonia of those three, because ammonia would have NH3 tendency not to lose anything so far, right? So far of those three, we would say the NH2 is the strongest. Then we got Cl-. Well, Cl- is an exceedingly strong, a conjugate base of an exceedingly strong acid, HCl. So therefore, it must be an exceedingly weak base. And the next one, so that means the amide ion is a stronger base than the chloride ion. But the next one is from a molecule which has no electronegativity differences as its conjugate acid. So it must be even weaker acid than anything else we've run into. Therefore, its conjugate base must be... Okay, so you don't even have to know the actual... Once you get comfort level with what's the strong acid, then you can walk your way through what's the weakest base, and so on and so forth. Okay, consider the following molecule having three labeled protons, same idea. Okay, first of all, let's get rid of the item that is the lowest acidity value. Something that is connected to, all three of them are connected to carbon. However, this one has to do, here's the shortcut to this. S character on the bonds. Remember S character? So a triple bond here has three, and this one has SP character, period. Right? This one here has, the next one here has, this is SP2 character. The next one here, and this one is SP3 character. So what percentage of this is S character? This is 50%, right? This one is 33%, right? And this one is 25%. The one with the greatest S character is the most acidic proton carrying carbon. It's the carbon carrying the most acidic proton. Because effectively the bond between the carbon and the hydrogen there breaks more easily. So if it breaks more easily, that means it can release an H+. It's a hetero breakage as opposed to a homo breakage, where the breakage would be between and equal amounts of electrons going to one side. In one case, the electrons go more to one side than the other. All right, list the following compounds in increasing order of acidity. This was meant to get you comfortable with acid and bases. All right, without going into too much detail, which is the strongest acid? D is in David, because that's an effect which is inductive in that case, increasing its value greater than B is in Bob, which is its analog, which has the same structure except it doesn't have a fluorine on it. Finally, the next one, so it goes D is in David, B is in Bob, C is in Charlie, and A as in Albert. Any questions about that? Consider the following reaction. Equilibrium for lies which way? To the right, because the weaker acid is on the right-hand side, which is the acetylene. The weaker base is the alkoxide anion. The stronger base on the left-hand side is the alkynide anion, and the weaker and the stronger acid is on the left-hand side, which is the alcohol, T-butylol. Questions? And the last one, the increasing from weakest to strongest would be D is in David. Chloride ion is weaker than hydroxide ion, which is weaker than amide ion. Got it? Questions?